diastereomers or the same. So press pause, work on this by yourself. When you're ready, press play. Okay, so previously we said that there's really a three-step process to answering a question like this. Number one is you want to look for the connectivity. You want to compare the connectivity of each of these two molecules. The second thing is to determine R and S for all stereocenters. And the last thing is you want to double check symmetry. All right, so usually we won't use this third step, but it does come into play occasionally, so it's important. Okay, number one is to just double check the connectivity of each of these molecules. So are they the same? 1, 2, 3, 4, 5. We've got 5 carbons on the left. We've got 5 carbons on the right. Notice how we've got hydroxyl groups at carbon 2 and carbon 4. We've got hydroxyl groups at carbon 2 and carbon 4. So we're not paying attention to stereochemistry here, just paying attention to connectivity. And they clearly have the same connectivity. Okay, the next thing is we want to be able to determine R and S for all stereocenters. So let's just make sure we can do that here. First of all, we've got to identify the stereocenters. Hopefully you can tell we've got stereocenters here, and we also got stereocenters here. Okay. And now we can always draw in the hydrogens, can help to draw these hydrogens in to make sure that we can see everything that's connected to these stereocenters. Whenever you're in doubt, never hurts to draw those things in. Okay, and then now we're going to calculate R and S. So what would be the highest priority atom attached to carbon number 2 here? Well, that should be the O, right? So O is number 1. And then we've got, well, the lowest priority should be the H, right? Now, attached here, we've got a carbon. We attach the carbon CH3, and we've got CH2 here. So I think you could probably see this immediately, but just to double check, put a little dot on these 2 carbons. And note that the carbon on the left is attached to 3 hydrogens, H, H, and H. And this carbon on the right is attached to 2 hydrogens as well as another carbon. Okay, so it's going to be higher priority. So this should be, this CHH beats HHH. So this is going to be priority number 2. And CH3 will be priority number 3. Okay, so let's just rub stuff out here to make it not as messy. And just leave the hidden hydrogens as they are. And so now we can figure out R and S. 1, 2, 3. Notice how it's going clockwise here. So that means that it's going to be R. Okay. Now over here on the other side, we've got OH is in the back, and this is priority 1. We've got this carbon priority 2, CH3 priority 3, hydrogen priority 4. So this is going to be going 1, 2, 3. It's going actually counterclockwise, but here our hydrogen is a wedge. So our hydrogen is actually in the back, in the front, instead of being in the back. So we need to flip it to go the opposite direction. And so if this starts off being counterclockwise, we flip it to clockwise, which makes it R. So this is RR, okay? Now we can do the same thing for figuring out R and S for the atoms on the stereocenters on the right. So this is priority 1. This is actually going to get rid of some of the numbers here. It's going to be confusing. So here's priority 1, which is the O, and then carbon's 2, CH3 is 3, hydrogen's 4. Notice how hydrogen is pointing out of the page. So whatever we get, we're going to have to flip. So if 1, 2, and 3 are going clockwise, now hydrogen's in the back, we actually have to make it the opposite, which is counterclockwise, so that would make this S, okay? And down here, we've got priorities 1, 2, 3, and 4. So this would be 1, 2, 3, and 4. We go in this direction clockwise. So this is R. All right, so we've got RR and SR. So the same connectivity, so they're not constitutional isomers. R and S, they are not opposite. They're not opposite. If they had to be exactly opposite, they would be enantiomers. But they're not opposite, therefore they're going to be diastereomers. So here, I said the same connectivity. Same connectivity, so they're not constitutional isomers. The RNS is not the opposite, so if they were opposite, they'd be enantiomers, but they're not opposite, they're diastereomers. Double check the symmetry. This is nothing we not need to do in this case. There's just one exception to, there's certain cases where molecules will have opposite RNS designations, but they'll actually be different versions of the same meso compound. And that's actually not going to come into play here. Okay, so not applicable. Although it is worth noting actually that this is actually a meso compound. If you were to look at the fact that the R and S is opposite and that you've got a symmetrical distribution of functional groups around the middle carbon, this is actually a meso compound drawn as a rotated version. But anyway, so these molecules here are diastereomers, and